All right, we'll start off with number 51 in the homework problems for this lecture. First one, A, what is the specific heat of water? If we're talking about the specific heat, we're talking about grams for this particular problem. And we're talking about water, and you're very familiar with this number. It is 4.184 joules per gram per Kelvin or degrees Celsius. So both these guys in the denominator. Now, if we change this over to molar heat capacity, we need to change grams into moles. So nice and easy for that. I will write that a little differently. And again, we'll have joules sitting here on top, and I'm going to kind of write it like this. So we have that obvious up and down. And if I want moles from grams, again, grams will go on top because grams on the bottom here. And I'm going to change it to moles. For every 1 mole, there are 18 grams of water. And this will give us an answer of something we rarely ever use, molar heat capacity. And that is 75 joules per mole per Kelvin. And again, rarely used, but there you go. What is the heat capacity of 185 grams of liquid water? Start off with what we have. 185 grams, and I just need to make sure that grams is going to go on the bottom of the line, so I'm starting with it in the top. So grams in kelvins or Celsius, doesn't matter, and I'll put the energy value, 4.184, on top of the line, and our answer is 774 joules, and in this case, only per Kelvin. That's a heat capacity. In other words, it takes this much energy to change 1 degree Kelvin or Celsius. Last one, D. How many kilojoules of heat are needed to raise the temperature of 10 kilograms of liquid water from that temperature to that temperature? Okay, so for this one, we could write E or Q. And I'm just going to write out the formula, which you guys are familiar with. And I want an answer in energy of kilojoules. So I have the heat capacity value from earlier. I'm going to use that here based upon the mass of the water, which we have in kilograms, so be careful with that. And then the change in temperature. Here we go. It is 4.184 joules per gram per Kelvin times, and the way I'm going to write this, it's 10 kilograms, which is the equivalent of 10, that's their number, times 10 to the third grams of water. So 10 kilograms. And then the change in temperature, I've already kind of done that math here. It is 21.6 kelvins. That's the difference between these two temperatures. And to put this as an answer, seems to be a fairly large number. 903,744 joules, which I don't really like. So I'm going to change that over to, because it specifically asked for it, kilojoules, 904 kilojoules. Done. All right. Let's switch over to a really fun topic that you may remember from last year. And that is, drum roll, Hess's law. So it's looking at reactions and then moving things around to create a new unknown reaction. We'll talk. Let's pretend you've got some carbon. You've got some oxygen that combine to produce some carbon dioxide. This is known. And this is actually called the heat of formation. And its value, typically like a canned value, is that much energy released in the process of the formation of carbon dioxide. And I have another one. I have carbon monoxide that will combine with half a mole. Again, these are heats of formation. Half a mole of oxygen gas. Also to produce carbon dioxide. So slightly different process in creating carbon dioxide. It has an enthalpy of formation of negative 283 kilojoules. I'm looking at making some carbon monoxide from slightly different materials than what are listed here. So the equation I'm going to look at, I'm going to leave us some space to do some work. I'll write the answer down first, the thing that the problem would probably give you, and say, let's figure out if we had carbon dioxide and we had oxygen, and we were producing carbon monoxide, how much energy would be involved in this process? We don't know, but we do have some things to work with up here. We could rearrange these equations and use coefficients in there if we needed to change these around, possibly flip these, and then apply a coefficient to it to change the value, and then rearrange them to make this equation. So we went over this probably in pretty good detail in lecture, but let's just see how it works. The way I would approach it is there's things that are going to cancel out, and there's things that may combine in this particular problem. To start off with, I look for things on either right side or left side. So I see down here that carbon is on the left side. So looking at these two equations, I look for carbon. There it is. It needs to be on the left-hand side, and it is. So I'm going to rewrite that exactly as it is. I notice there's a 1 in front. There's a 1 in front up here too. So that is exactly how it needs to look. So I don't need to make any changes at all. And I know what you're thinking. It's like, this looks really easy. I think I can do this. Oops. All right, that one's done. Now for the second one, I noticed that I don't have carbon dioxide written down here at all, which means it canceled out. Well, here it is on the right, meaning it needs to be on the left, so I can cancel them. And then also, maybe you can see this, maybe you can't. I have a half an oxygen here, and I have a whole one there. Therefore, something needs to cancel half of this out. So this oxygen needs to be on the other side. So really what I'm talking about is this equation here needs to be flipped. Carbon dioxide is on the left, it needs to be on the right. Everything just goes with that pattern. So let's rewrite this equation, but backwards. Carbon dioxide gas produces carbon monoxide gas and half of a oxygen gas. And then I have an energy value, but it's the opposite because I flipped it. So it's a positive 283.5 kilojoules. All right, now it's just math, just kind of adding things up and canceling. CO2, I've got 1. CO2, I've got 1. It's gone. 1/2 oxygen, this is gone, and this is replaced with 1/2 remaining. This drops down. This looks a lot like that. This looks a lot like that. It drops down as well. Now I just need to add these two values up, and I'm left with the remaining 110. Again, this was unknown. 110.5 kilojoules of energy for this reaction that we did not run, but based upon known information, we now know the energy value involved in the process. There it is. Now, if we're in class, we'd actually do a whole worksheet on this, but we do have one in the homework that we can do, if I'm not mistaken. So let's do that. It's number 63. So here it is. I'm actually going to pause right here. It's a good place to take a break, and we'll have one more lecture after this one.